This video is going to cover 1.6 chemical equilibria from AQA A-level chemistry, focusing on an introduction to equilibrium constants. This video is going to cover what are equilibrium constants, an introduction to Kc, Kc expressions, units for Kc expressions, and quantitative changes in Kc values. It's also worth noting that at A-level you will only be asked to look at equilibrium constants for homogeneous systems. Those are systems where all species are in the same state, for example all gases. So far, you've probably only looked at changes in equilibrium position in a qualitative way. For example, equilibrium shifts left, increasing the yield of products. Qualitative means without numbers. So statements talking about movement of quantities without actually using quantities. However, we can look at equilibria quantitatively using numbers and perform calculations to work out how much the position of equilibrium has shifted. Any system in equilibrium has a constant for that equilibrium associated with it, which can be thought of as simply a value linking how much product and reactant is present at equilibria. It's almost as simple as it being a ratio. These constants are denoted using a capital K, and as long as the specific reaction conditions remain constant, so will K. K can be expressed in a variety of ways for a variety of different chemical parameters, but at A-level the main ones are concentration, Kc, and pressure, Kp, which is studied in Year 2. The equilibrium constant for concentration, Kc, is written as an expression using the concentrations of the products and reactants present at equilibrium. Now we have a general format for this, and Kc is always the concentration of the products divided by the concentration of the reactants. Now in chemistry, square brackets means the concentration of the species inside the bracket, always, and we must use square brackets for Kc expressions. And if we have multiple products or multiple reactants, it would be the product of those. So we would times them together on the top and on the bottom. Now, if we have a balanced chemical equation, the mole ratio of the reactants and products does have an effect on the expression. Each species in the expression is raised to the power of its stoichiometric ratio in the balanced equation. Now that might sound a little bit complicated, but it is fairly simple. For example, for the reaction AA plus BB in equilibrium with CC and DD, where the lowercase letters are the number of moles of each, the stoichiometric ratio, the Kc expression would be Kc equals the concentration in square brackets of C raised to the power of little c, whatever that number is, times by the concentration of D raised to the power of little d, divided by the concentration of A raised to little a, times by the concentration of B raised to the power of little b. Now the equation that's on screen at the minute is really common for A-level exams. They use it a lot for calculations and examples, and it's the reaction of hydrogen gas and iodine gas to form hydrogen iodide gas. Now if we were to write this as a Kc expression, Kc would be the concentration of the products, which is in this case Hi, so we'd put Hi in square brackets, raised to the power of its stoichiometric ratio, which is 2, so it would be Hi squared, divided by the concentration of the reactants, which would be H2 in square brackets, and I2 in square brackets, and that would be the Kc expression. If we had the concentrations at equilibrium, we could simply put them in to that expression and we would get a value for Kc. But we also have to consider what would the units of Kc be for this reaction. Concentration is measured in moles per decimeter cubed, and it will always be measured in moles per decimeter cubed for Kc. Now we have a number of concentration terms here, so we have to think what would the overall unit for Kc be. Now Kc, they are it's not a universal constant, so it doesn't have a set unit each time. We have to derive the units from the number of concentration terms that are actually in each individual expression. And there will be a different unit for a different chemical reaction, as the stoichiometry will be different. So for this particular one, on the top, we can see that we have two concentration terms. We have HI concentration squared. So I've put here moles per decimeter cubed in brackets squared. On the bottom of the fraction, we've got two concentration terms, moles per decimeter cubed, moles per decimeter cubed. Now we've got 2 on the top and 2 on the bottom, and we can see that slightly more clearly if I expand out the top to be moles per decimeter cubed times moles per decimeter cubed and get rid of the squared. We can see now that we have 2 on the top and 2 on the bottom, so they all cancel out. So actually there will be no units for this particular Kc expression. If ever you're asked to state the units and you work out that the stoichiometry is equal, in this case 2 moles on the right and 2 moles on the left, it is really important that you write that there are no units and don't just leave the gap blank. So looking at another example here, another common one, what would the expression for Kc be with units for the following esterification reaction? Feel free to pause the video and have a look. Well, for this one, it would be Kc is equal to the concentration of the products, which in this case is CH3, COO, C2H5, that's ethyl ethanoate if you were to draw it out, times by the concentration of the other product, which is water. This is a condensation reaction, divided by the concentration of the reactants. So we have ethanol, C2H5OH, and ethanoic acid, CH3COOH. Esterification reactions are really common for Kc. Now in terms of units, if we look here, we can see that we've got 2 concentration terms on the top and we've got 2 on the bottom. They'd both cancel out and there would be no units. Now just a couple of little points here. Make sure that you do use square brackets and that they definitely look square. Mine look a little bit wobbly. You can get away with them being a little bit not defined, but if you were to put a curved bracket, it would be marked wrong. And the other thing is make sure that you get your chemical formulae correct inside the brackets, because if you make a mistake in any of those organic chemical or any chemical formulae, then the expression will be marked wrong, even if it's a small mistake. So make sure that you do check that you've got the right number of C's, H's, O's, etc. So, time for you to have a go. Activity 1. Write expressions for Kc for the following reactions, giving the units for each one. There are 4. So, as always, pause the video here, have a go, and then the answers will follow next. So, answers for these. First example we have is a reaction that should be fairly familiar, N2 plus 3H2 in equilibrium with 2NH3. That is the formation of ammonia, and if we had specific conditions, it would be the Haber process. So Kc for this reaction will be equal to the products, which in this case are NH3, just NH3. So we have 1 on the top, but it is 2NH3, so it's NH3 squared. And then we divide that by the concentration of the products. So we have N2. There's only 1 of those, and then we have 3H2, so it's H2 cubed. So that's the expression for Kc, products over reactants, square brackets, and correct powers. Now the units, a little bit more tricky for this one. We've got 2 concentration terms on the top, so we would have moles per decimeter cubed, because it is NH3 squared. And on the bottom, we've actually got 4. We've got moles per decimeter cubed for the N2. And then we have 3 terms, slightly dodgy 3 there. So we have a total of 4 on the bottom because we have 3 moles per decimeter cubed terms from the H2. So the 2 on the top can cancel out 2 on the bottom. So we end up with 1 over moles per decimeter cubed, moles per decimeter cubed. Now that is equal to moles squared, because moles times moles would be moles squared, and that would be dm minus 6. Now if you remember your rules from GCSE about indices, if we're timesing indices together, we actually add the two indices. So dm minus 3 times dm minus 3 is actually dm minus 6. You add the two together. Now, in order to get rid of a fraction, we're looking at units, what we do is you can turn the fraction upside down and we can put the 1 on the bottom. And what we do there is it turns the moles squared to be moles minus 2, and the dm minus 6 becomes dm plus 6. So that's how we can get rid of a fraction. And so the units for this would be moles minus 2 dm plus 6. Question 2, Kc would be, again, the products of the reactants, which in this case we only have one reactant, so it would be CoCl2 squared because it has a stoichiometric ratio of 2. And then we have carbon monoxide squared times Cl2 squared. So that's the Kc expression there, products over reactants. Now what we have is we have 2 concentration terms on the top and 4 on the bottom. So we would end up with, if we cancel out the 2 on the top with 2 on the bottom, we would end up with 1 over moles 2 dm minus 6 as on the previous slide. So we could write it all out again with 2 moles per decimeter cubed on the top and 4 moles per decimeter cubed on the bottom because we have 4 here. But it would be the same as the one on the previous slide. So the units for this one again are moles minus 2 dm plus 6. You don't have to put the plus 6 there, you can just write 6, but I like to write the plus just because it reminds me that it is, that I have taken into account that it's been inverted. For number 3, Kc would be the concentration of the products, so O2, and it's cubed because it's 3O2, divided by the concentration of the reactants, which in this case is O3, and that is squared. Now this is a reaction that you should recognise from your depletion of the ozone using free radical substitution mechanisms. Anyway, what we can see here is that we have 3 concentration terms on the top, so moles per decimeter cubed, and we have 2 on the bottom, so we have squared. Well, the 3 can cancel out all of those and we end up with 1 left. So the unit of this one is just moles per decimeter cubed, because the 2 on the bottom cancel out 2 of the ones on the top, leaving 1 on the top. Question 4, 2 NOCl forming 2 NO and Cl2. So Kc will be concentration of NO squared times the concentration of Cl2, just one of those, divided by the concentration of NOCl, and that is squared as well. And the unit here, well, we've got 3 concentration terms on the top and 2 on the bottom, so 3 and 2, well, that would cancel out, we'd end up with just 1 on the top. So that would just be moles per decimeter cubed. So moving on to look at quantitative changes of Kc. The only thing that affects the value of Kc for a specific reaction is the temperature. A common exam question is, what would happen to the value of Kc if a catalyst was added? What would happen to the value of Kc if we change the concentration? Well, once you've got a set value for Kc at equilibrium, the only thing that will change that value is if you change the temperature. And we're going to have a look at how temperature and why temperature changes Kc. So again, we're going to look at our common familiar reaction of the Haber process, N2 plus 3H2 in equilibrium with 2NH3. And this time I've given you some enthalpy data. So we've got here that the delta H for the forwards reaction is minus 93 kilojoules per mole. Now, if we remember from the previous video, a negative delta H means exothermic, and these delta values are always given for the forwards reaction. So this is telling us that this forwards reaction is exothermic and would cause therefore temperature to go up in the forwards direction. The opposite is therefore true for the backwards reaction, that the backwards reaction would be endo and cause the temperature to go down. Now, any time we're dealing with equilibrium, we need to think about Le Chatelier's principle. So that's something really important just to keep in your mind. Now, what I've got here is a little table of data showing the Kc values for a variety of temperatures. And you can see that temperature is increasing as we go down this table. I should probably put that in red. Now, what we have to do, if we're talking about values of Kc, is we have to think about Kc. Now, we just did this as an example, but Kc for this particular reaction is the concentration of NH3 squared divided by the concentration of N2 times the concentration of H2 cubed. We can see the unit is already in the table, moles to the minus 2 dm6. Now, if we think about this reaction, if we look at this table with temperature increasing, if we use Le Chatelier's principle and think what happens to the equilibria as we increase temperature, we can think this through quite clearly and see why Kc changes. We know that the forwards reaction is exothermic. And so if the temperature is increased, the backwards reaction will be favoured because that is endothermic and it will decrease the temperature. So if we increase the temperature, the endothermic reaction will be favoured. Now, if we favour the backwards reaction, that means that we are making more of the reactants, and the concentration of the reactants will increase. Now, what that will do is increase the bottom of this fraction. So if the bottom of the fraction increases, the value of Kc will go down. We can see that here, that it goes from being 10 to the power of 1 to 10 to the minus 4. So it's specifically related to whether or not the forwards reaction is exothermic or endothermic. So activity 2, your turn again. I'm going to give you an exam style question, and it's a very common type of question that comes up for these types of questions for Kc. So state and explain the effect on the value of Kc for this reaction if temperature is increased. In your answer, you should refer to the expression for Kc for this reaction. As always, have a go, pause the video, and the answers will follow. Okay, so looking at the answers then. First of all, just have a think about the question. State and explain the effect on the value of Kc for this reaction if temperature is increased. Now, always use your exam technique and think through the question really clearly. It says in your answer you should refer to the expression for Kc. So that's a really important thing that people tend to miss, is that if they say refer to the expression for Kc, you need to use the expression for Kc. So we'll do that first. Kc is the concentration of the products, which is in this case NO, and we square it because it's 2NO. We're going to divide that by the product of the concentration of the reactants. Remember, product just means times. So N2, and that's just stoichiometry of 1, and we have O2, again, stoichiometry of 1. So there will be no units here, so that's something just to bear in mind. We have 2 concentrations on the top, and we have 2 on the bottom, so the moles per decimeter cubed would cancel out. Now, thinking through this chemical reaction, we've got here a positive enthalpy change. Now, positive means endothermic in the forwards direction. So we would be looking at the forwards reaction being endo and causing a temperature decrease. And we would also then, in the reverse direction, have exo, which would cause the temperature to increase in the backwards direction. So our particular question is saying if temperature is increased, if we increase the temperature. So if temperature is going up, what will the reaction do in reverse? Well, now that we've thought through that information, we can have a look at the answers. As temperature is increased, the forwards reaction will be favoured as this is endothermic and will decrease the temperature. So equilibrium would shift to the right, which we said originally. We've got here this right-hand forwards reaction being endothermic. Remember, with these explanations, you always have to say what will happen. In this case, the forwards reaction will be favoured and why. And the why here is that the forwards reaction is endothermic and it will oppose the increase in temperature by decreasing it. So if this is happening and we've got the forwards reaction being favoured, then what we have here is an increase in the concentration of the products because we're favouring the forwards direction. So we will get more NO, which means the top of our fraction will go up. And therefore, Kc will increase with temperature. And what I've got here is just a little table of results here to prove that. So we've got here that the temperature is going up. T increases as it goes down the table. And if we look at the value of Kc, Kc is also going up as we go up with temperature. We go from a 10 to the minus 13 to a 10 to the minus 5. Still tiny, but not as tiny as 10 to the minus 13. Kc can have any value. It doesn't matter. There's no sort of range of data that we're looking at. It can be very big, it can be very small. But there we go.